Hello everyone, myself Dipti Gusse. I am working as assistant professor in School of Computer Engineering at MIT Academy of Engineering Alandi Pune. Today's discussion on the demonstration for pneumonia detection using convolutional neural network. This is the case study for binary class classification. As all of you know, the pneumonia is an infection that inflames air sacs in one or both lungs. Doctor can detect this pneumonia based on the chest X-ray images, and uh, they can detect whether that person having a pneumonia or that chest X-ray is normal chest X-ray. Now here, the task for this demonstration that detection of pneumonia based on the chest X-ray images using convolutional neural network model. Now for this example, we are using Keras libraries under TensorFlow. We are using sequential model and the layers which are included in the CNN model. As previously in the previous recording already we have discussed what is the convolutional neural network and how these layers are added for the for training and testing purpose. Also in this libraries we are adding image data generator for the data augmentation, classification and report libraries and confusion matrix for the evaluation of the model, and reduce LR on plateau to monitor the learning rate during the training. As the data set we are using for this example, that is chest X-ray. Now chest X-ray images. Now this chest X-ray data set is available on Kaggle. Now there are two classes for normal and pneumonia. In data set there are three folders: test, train and validation folder. In each folder again there are two folders which consist of normal as well as pneumonia images. There are two folders, and in normal folder contain the normal images and normal chest X-ray images, and in pneumonia folder contain pneumonia chest X-ray images. Now here in this example we are adding the embedding the Kaggle environment in Google Colab notebook. Here you can connect the Kaggle environment with Google Colab by giving the username and Kaggle key. This Kaggle key you can generate through the Google Kaggle account. Then once you connect Kaggle environment with Google Colab, then select the data set, required data set, and copy its API and paste in cell, Google Colab cell. Means here you are connecting Kaggle environment through the Google Colab and adding the downloading the data set which is available on Kaggle, and this data set temporarily available on the Google Drive. Now here next, once we run this model, then your data set is available on downloaded, that zip file will be downloaded on your content drive, Google Drive. Once you download this zip file, then you can download this zip file, and here you can see the zip file. Now this is the zip file, and then after unzip you can see this test, train and validation data set. Okay, now this test contain the normal and pneumonia images. Same way train and validation also contain these two folders. Normal folder contain the normal test X-ray images, and pneumonia folder contain pneumonia chest X-ray images. Now your data set is ready on Google Drive. Now there are two classes, pneumonia and normal. Now we have to set the labels for these images. The images available in pneumonia folder, give the label to these images as pneumonia, and the images available in normal class give the label as a normal. This code for the this is the user defined function get data. By using this you can pass the directory, train, test and validation directory, and you can give the label and arrange the data set for the training purpose. Now once you call this function, now here give the path. You can give the path from here Now suppose you are using this test, then click three dots and you can copy the path and paste it here. Okay, now once you execute this get data function for the three folder train and test validation, then here all labels will be assigned to the images which are available in these folders. Here you can also display the pneumonia image using matplotlib. Now these are the pneumonia sample x-ray images and these are normal x-ray images. Then you can also display the length of the number of images present in train, test and validation. Using get data function, you taken the all images in these folders from the folders. Now there are 502,000 images are present in train data set. 624 images are available for testing purpose and 16 images are available for validation purpose. Next two counts with respect to the images belongs to pneumonia class, and 1341 images belongs to normal class in training folder, in training data set. This is the distribution of both classes. As this data set seem imbalanced, to increase the number of training example, we can use the data augmentation concept. Now here you can display the figure wise one by one image you can display by adding the grid in an image. Now let us discuss now how here then next step, that is the pre-processing. Now in pre-processing, we are pre-processing the input images by dividing this the pixel information, that array of pixel of images divided by 255 and we are normalizing the pixels of the images available in train, test and validation folder. 255 we are divided by 2, these values are normalized 255 as the pixel value range from the 0 to 255. Then we are reshaping the train and validation and test folder, test data set as here after reshape. Now here this is the reshape data set, train data set dimension. 5216 images are there, each image having the height and width, that is 150 150, and that there is as these are the grayscale images, so number of channel is 1. Same for testing. Also we are displaying here 5216 and 600 224. These are train and test levels respectively. Now here we are increasing the training example by adding the concept of data augmentation. Through data augmentation, we can zoom image, shift image horizontally, vertically, flip image horizontally. Now and we can increase the data set. Now using image data generator, we can utilize the function. You can apply the data augmentation and increase the data set. Now here. Now let us discuss next concept, that is how we are using the CNN model for the implementation. Now this is the example, this is the architecture of CNN. As already in previous lecture we have discussed the working model of CNN architecture. As here we'll revise in 2 minutes. The input is given. Now this input is given to the convolution layer. Now here input image passed through the various convolution layer, max pooling layer, then image extracted features are flattened and give as input to the dense layer. Now this is all about, now this is the CNN model. As here we are importing sequential models dot sequential. In sequential model we are adding number of layers. The output of one layer will be the input for the next layer. Okay, now first here we are, as per the architecture of the CNN, we are adding the first convolution layer, that is con 2D, that is for the 2-dimension images. There are 32 filter. That first value is respect to the number of filters and next value is a 3 by 3, means 32 filters we are using in convolution layer where the size of filter is 3 by 3, stride is equal to 1, and here we are using same type of padding, and activation is equal to ReLU. Using activation of ReLU, whatever operation of the convolution, if that value is negative less than 0, then that value it will be set to 0. Input shape given to the convolution layer is 150 by 150 by 1. That is 1 is the number of channel and height and width is equal to 150. Now after that we are using the batch normalization. Actually batch normalization is not a part of convolution layer, but this batch normalization layer we are adding to normalize the value which is written by the previous layer. Next layer, after convolution layer, we are adding next layer, that is max pooling layer. Max pool 2D. These are we are using for the two-dimensional images. Max pooling layer. In max pooling layer, we are using the 2 by 2 filter to reduce the dimension of the features. Now here 32 feature maps are generated using convolution layers, and then here max pooling layer is applied on convolution layer output with stride 2 and padding is equal to same. Then here in this code, we can add n number of convolution layer and n number of max pooling layer. Again, it depends upon how we are using, what type of data set we are selecting. The dropout layer we are adding here to reduce to deactivate some features in convolution layer, and here 0.1 is means the 10% of features we are deactivating. Okay, now the features generated by the previous layers, these features will be deactivated and ratio is 10%. Okay, generally this dropout layer we are using to avoid the overfitting. Next, now here in this example we are adding 1, 2, 3, 4 and 5 convolution layer and 5 max pooling layer to capture the features from the images. Once you once you add the last convolution layer, then after that last max pooling 2D layer, then here in last convolution layer there are 256 features filters are used. So 256 feature maps are generated and its size will be reduced by max pooling 2D layer. Now once the features are ready, then these features are flattened, means these all 256 features will be transformed into one linear vector, and these features linear vectors we are passing through the next neural network model. Now here neural network, these are hidden layers of the neural network, which is called as a fully connected layer in convolutional neural network. In this example, we are adding one fully connected layer and one output layer. Now we are adding this fully connected layer by adding the dense layer. In dense layer, in fully connected layer 1, there are 128 neurons. 128 neurons are there, and we are using a ReLU activation function to activate the neurons in a model. Now dropout layer also we are using in fully connected layer, which is used to drop out to deactivate the neurons. Now here 20% neurons are deactivating. Now last layer, that is a dense layer, that in dense, that is the output layer. When unit is equal to 1 means only one unit is only that is this is example of binary classification, either pneumonia or normal. So only one neuron is available in output layer, and activation function is sigmoid, as it is the binary class classification. RMS optimizer we are using for the compilation. Loss we are calculating using binary cross entropy, and metric for as an accuracy, which is defined for the evaluating the performance of the model. Now here you can display the summary using model.summary. Now this is the summary of model. You can see these are the output generated after the each layer, and these are the parameters involved in a CNN model. You can also go through these references for the practice purpose. Here next concept, that is called as the learning rate reduction. Here in this code we are trying to reduce the learning rate if accuracy is stable. After 1 or 2 epoch, accuracy there is no change in accuracy. Now in this case we can decrease the learning rate up to minimum learning rate 0.0001. We can monitor the validation accuracy. Based on this, you can decrease the learning rate. Now here this is the now here we are training the model.fit data gen, as already we are created the function for the data augmentation. Now this data augmentation function we are applying on Y-train X-train data set, as so we are applying this function on validation data set to increase the data set size. Now this model is for practice purpose. We train this model only for 1%. You can increase the number of epoch. As number of epochs are increasing, there may be chances to increase the accuracy and reduce the loss. Now here the accuracy of this model is accuracy is 0. For train test accuracy is 0.88. For the epoch 1 and loss is equal to 9.00. As here you can increase here increase the accuracy of model by increasing the number of epochs. Now analysis after training, you can analyze the after training and you can plot the graph, and here you can train this model for the number of epoch. Now you can see in this example here for 12 epochs the model is trained, and you can see the loss and accuracy for training and testing. You can see also the effect of reduce LR plateau function. If accuracy is not increasing, in this case the reducing, we can reduce the learning rate, and here the number of steps will be decreased. Now this is the graph training validation accuracy, training and validation accuracy for graph, and this is the testing accuracy. You can see here training accuracy, as the number of epochs are increasing, the accuracy is increasing. Okay, here this is the training accuracy. The training accuracy is increasing as number of epochs is increasing. Here in validation data set only 16 images are there, so here that accuracy is not up to the mark. But here you can see for trained data set accuracy, training loss and validation loss, you can see this diagram, the loss is decreasing as number of epochs are increasing. Then once you execute this model, you can display the classification report, and you can also display the confusion matrix. Once you train this model for 20 epochs, 30 epochs, as per your based on your accuracy, once you complete your training, then you can save the weight of the model by using and save the model using model.h5. So for the next time, and save this model on your disk. Whenever you want to test any image for predicting the pneumonia, for detection of the pneumonia, you can use this already pre-trained save weight model, so that you can save the time which is required for the training purpose. This is all about how we are using the CNN architecture for pneumonia